Hello, welcome back. So we're back now with biostatistics. We are in class 11. I'm sharing my screen here. So we have spoken last week about maximum likelihood estimation for logistic regression. We talked about sensitivity and specificity and the receiver operating characteristic curves. I hope the lab was all okay and you were able to tackle the challenges. I didn't receive any discussion board entries, so I conclude from that, but yes. So today we're going to go into the next topic, and it's only 3 more topics, right? So we're talking today about the introduction of potential outcomes, propensity score methods, and propensity score matching methods. And this is actually very interesting topic, and actually I worked on several analyses on the topic, and one actually got published on the comparison of the prescription of different dialysate sodium prescription algorithms, and it's kind of an interesting approach because essentially what it allows you, and I'm just quickly give you the narrative why we chose to do that. So the idea is really that you can treat a regular cohort study, an observational cohort study, in a way as if it would have been a randomized control trial. Obviously with reservations, with still unaccounted additional confounding. And we will talk about this today, but there are actually strong opinions in the epidemiology community that actually all observational data should to some extent be analyzed that way. And yeah, so we have as additional reading for the topic, we have the Rubin paper that basically speaks about the mediation analyses and the importance of confounding models and to account for confounding. And then we have the Rosenbaum paper that essentially elaborates on the propensity score per se. So, but I have now essentially here Professor Sang's lecture open. You all have received the RMD file, so this should be downloadable from the respective class tab. And you can now open up the PDF. So I hope this was without problems. I did see that's the wrong one. Wrong folder. That's the original folder. That's okay. So this is essentially the lecture for today. I have this and full screen view. Okay. So we're talking about class 11. This will be about propensity score methods for causal inference. We will be discussing potential outcomes. This is just giving a first brief idea about potential outcomes and what that actually implies and means. It's just a briefing. More will be in the next class, and we will talk about matching in its simplest form. Propensity scores can serve the matching of data to minimize confounding, and we will look at this in a second. The example is actually very good that Professor Sang has chosen, and it's very illustrative and very educational. So I'm sure you're going to like this one. So lab 11 will be talking about the help RCT data, just like the main lecture analyses that will be shown. And we are again doing the same thing. We're examining covariant balance and matched sample, the same as we do during the lecture now. Okay, so we do have in observational studies, we do have 3 dimensions, right? So the first is really, the most important thing is the observed outcome. So we have an outcome that essentially we have seen in a cohort study, and we are interested to what extent this differs between both cohorts. So we have, and this is the definition of a cohort study, right? It comes from ancient Rome, where essentially a cohort was a group of, I believe, 500 individuals that would march towards the enemy and go to battle as a cohort. So essentially, this is essentially what happens in a cohort study. So you basically have your two cohorts. You have the zero cohort, the control cohort, and the one cohort, which is a intervention, quote unquote, observational intervention cohort, which does have the exposure of interest. And you observe these while they're marching forward in time, chronologically marching. And you are then analyzing the outcome over time. So now on the way, there will be a lot of things happening to these two cohorts, right? And this is not even going that far that you will have disbalances from people moving away or whatsoever. No, it starts as early as baseline, where essentially the balance between both groups, and we know that, right? We know that from the RCT lectures. The balance between both cohorts at baseline will determine to what extent confounder will play a role. So now this being said, this gives us here already the third dimension. So we have covariates, and these covariates essentially comprise mainly of baseline characteristics like age, gender, medical history, environmental factors, genetic factors, in addition to those that may happen during the course of the study, but these are harder to quantify essentially. So in most cohort studies, you cannot really do much about the changes in time, except for when you work with time varying coefficients, but even then you only can to some extent account for them. So confounding is really kind of problematic, and we will see why. So the interest that we have here is the causal inference between X and Y. So we want to know to what extent the interventional comparison characteristic, comparative exposure, the exposure that causes the interest into this comparison, affects the outcome. This is the causal inference, right? So, but we're not really looking at this as an association. So it's not a correlational kind of setting, it's a comparative setting. So essentially we want to know whether the Y of outcome in the Y, so this is the outcome, in the exposed group minus the Y, again the outcome, in the unexposed group is the same or is different. So now let's stick with a continuous outcome for the simpler fact of this kind of application. So we have here the example given by Professor Sang is that homelessness, X, which essentially is like a binary outcome. So you could think of some innovative way to make this a continuous outcome. It is a binary outcome. You're either homeless or you're not homeless. So homeless and the association to high depression. So is homelessness causing high depression? Several arguments to make is like definitely it could also be, could go in both directions, right? Hypothetically, I could see a bidirectional kind of setting, but that's going to philosophical at this point and speculative. So essentially homelessness causes high depression. Why? So high depression being the continuous variable quantified in the HELP RCT data using the CESD, which is a depression scale. So there are various depression scales out there, and you are looking at a continuous variable that is being determined by a binary variable, homelessness. So now yi and y0 is now essentially the outcome if the subject is assigned to a treatment, in our case, homelessness. Y0 is the outcome if a subject is assigned to the control group, which is no homelessness. So we have here subjects, Joe, Mary, Sally, and Bob. So there are 4 subjects. They have their baseline variables, and they have a Y1, Y0, and essentially we have to conclude based on our observed yi1 and yi0 whether there's a difference between yi1 minus yi0, and whether this is actually different from 0. So now you're going to say, well, this is simple, right? It's a random sample statistic. You just take whatever individuals you have. You basically employ the concept of an independent sample t-test. You draw random samples and random sample that comes from the other group. You calculate the difference, and then you basically build the distribution of the sample means. Yes, and that's true. But the point is, you may have differences between homeless and non-homeless people that you are not taking advantage of. So essentially, if you are comparing just the sample means and you are only comparing these, there may be unaccounted confounding contained in this difference that you're seeing that you are not basically accounting for. So this difference is obviously it's either you're homeless or you're not, so that's a counterfactual. And these baseline characteristics do essentially affect the balance of these covariates within the groups. So homelessness, it's more likely that you're male when you're homeless. It's more likely that you essentially have depression already to start with. It's more likely that you don't have a job, obviously. And so there are many dimensions that essentially lead to homelessness. And to balance these out is the only way to understand the true difference between homeless people and non-homeless people in terms of the continuous variable depression. So only then you really can draw a causal inference. So we have talked with RCTs about causal inference. And the only way how you can draw causal inference is to essentially take the confounding into account. So if you don't take these confounders into account, essentially you will end up with a confounded outcome, and confounder being something that associates with the outcome as well as with the exposure. So if this informs them both, your difference will essentially be either subject to type 1 or type 2 error. So if you're matching them, you can match them on various covariates, right? So there are various ways how you can match. So this is not the only way, right? So propensity score matching is by no means the only way. You can use other matching algorithms like Mahalanobis metrics. And essentially, the principle is the same. You pick covariates and you match based on these covariates. You can also just define ranges within which you're willing to accept people that are exposed. So you take the larger group and you or you take the smaller group and you pool from the larger group and you kind of get more of an artificial kind of balance that could be considerably balanced, but sometimes is not. And only with propensity score matching, you essentially get a very balanced kind of cohort setting. So the intuition is really that you would like to distribute between homeless and non-homeless, and to have the covariates balanced in a random fashion, and in order to mimic random sampling and randomization at baseline. So let's look into this. So why is this useful, first of all? It is useful because you may only have observational data at hand, and you are not able to manipulate your exposure. So you can not really. So this is true. For example, this is things that are traditionally ethically hard to defend. It's like, this is a very good example. You can't randomize somebody to be homeless or not homeless. So this is, although on some population studies, you hypothetically could get like this quasi-experimental kind of studies. But in essence, you cannot randomize this as an exposure, right? You can just not do that. It's the same with lifestyle studies where, for example, you can't really randomize somebody to start smoking or to randomize somebody to drink like 2 pints of beer. Right? These are just things that are ethically not doable. There are things that are practically not doable. There are things that are logistically not feasible. So it really comes to the status whether this is manipulatable or intervention randomizable. So it's really it's by default it will always remain an observational study. However, it may not be manipulatable, but it is definitely predictable. Meaning then that when you have large enough crowd, or when you have a large enough sample, you can try to predict the status of your exposure. So you can predict for the homeless, being homeless is predictable, and whether you can use this to build a function to essentially predict that and use that for insights to match it with your control cohort. And this is essentially what the propensity score does. So we could match on all covariates. Then we get a smaller sample that is homeless, and we get from a large pool of non-homeless people, we get like a subset, and they may be balanced, and like a lot of manual work, right? Well, it's not manual, but it's nevertheless it's still not going to be balanced. What you can do, and this is the intriguing aspect of it now with the propensity score, you get here balanced weights between the covariates, and you quantify the probability of being homeless based on the background covariates that you have at hand. So you are aiming to predict you're working to predict your exposure. Based on that, you will get a probability value, and for that, please see the Rosenbaum paper. This is a probability between 0 and 1. So if we have now, in a perfect world, we would use so many covariates that we get an exact probability for both drug users and no drug users, homeless and non-homeless, smokers and non-smokers, alcoholics and non-alcoholics, you name it, right? So if you are getting a probability for 2 individuals that is entirely the same, and you're comfortable accepting this probability as being the true probability, which obviously is the downside of the methods, right? And then you have a random effect causing one to become a smoker, or one to become an alcoholic or a drug user, whereas the other is randomly not a drug user, smoker, an alcoholic. So this randomness is obviously debatable, because you will always have residual confounding that you don't have the data for it, you didn't think of it, it cannot be quantified, it's genetic, it's some higher unaccountable factor. And this is the beauty, right? Because with an RCT, you have an adequate sample size, hypothetically you have randomness due to the randomization. So the matching is actually by design, and it's not something that you retrospectively tried to implement and to kind of gather from your data. So this being said, and Professor Seng is here alluding to the so-called table 1. So the table 1 is like this descriptive kind of comparison, right? So you compare characteristics prior to start of your follow-up time, or your outcome, and you essentially try to test for the balance between those groups. So you compute this table 1 that essentially gives you insights into what extent these cohorts are significantly different from each other, and to what extent they may have been residually confounding. So this is what the table 1 is referring to. Okay. So in principle, if two people have the exact probability, the assumption for propensity score matching is that then the assignment to either exposure group, smoker, non-smoker, alcoholic, non-alcoholic, drug user, non-drug user, is random. So let's accept this as that. And let's move on. Okay, so we have 1O has the outcome. This is Joe. Then we have 2O, that's Mary 0. Then we have Joe 1, Joe 2, Joe 3. And we're matching now. We're matching people that do not have the exposure, the YI0, based on their propensity score, so which is for all 4 Joes, 0.95. So this is the probability to be in the homeless group. So now we have, as I mentioned before, it's more likely for a man to be homeless. So we have here Mary. Mary has only a probability of 0.13 to be homeless, and she also has high school. So in addition, so now she's now associated with 17, 29, 44, 23. She's basically here at a certain probability, right? So we are calculating now these, so YI is the outcome. So this is the CESD depression score. So we're getting the score entries. These are obviously estimated numbers. So we have here Joe, which is a homeless individual, with 25 minus the non-homeless people, 4, 7, and 10. And then we have Mary, who is not homeless, matched with homeless people, with Mary 1, 2, and 3. So we have 29, 44, and 23. So the homelessness is indeed somewhat higher in those being homeless. So how to get the propensity score and how to do the matching. So, but I think the principle here is clear, right? So we just mean to kind of go an additional step with the matching, but basically match on the probabilities to have a certain exposure and to kind of reduce residual confounding, and by that essentially establish an individual causal effect, and to go one step further toward establishing causality, even with an observational data example. So, okay, so you can do this with a logistic regression, right? So the logistic regression will allow you to get the odds. From the odds, you get to the probability, and essentially you can use the exposure, this binary exposure, as the response variable, and the baseline characteristic as covariates or predictors. So obviously, I think there's a cohort study. This allocation to either cohort needs to be binary. It can be more groups, but then it's getting more complicated, and this gets a whole different conversation piece, because then you need different models, and you need to match not only one with another, you also need to match others with another. So it's becoming much more tricky. But now for the simplest example, this is what you need to know. Logistic regression, homelessness is the response variable, baseline characteristic serves as the predictors of this exposure being predicted. So how to do the matching, that's a little trickier. So this is, you get a probability, and based on this probability, you need to predict the exposure. How do you do that? Well, there are various ways to do that, and there are different algorithms to approach that. The one we are doing here is nearest neighbor, which is kind of the nearest probability, so to say. It has nothing to do with the AI algorithm, so it goes in the same conceptual way, but it's a different concept. So we will now look into such a confounding model by using the help RCT data, and we have the outcome depression, and the study variable is homelessness. So we describe now the outcome variable for the entire sample and by each group of the study variable. So outcome variable is now essentially entire sample, and then we're looking into the groupings, homelessness versus no homelessness. Continuous variable are now essentially characterized with the normal measures of central tendency and variability in a standard deviation. And it's always good to plot and to do proper descriptive statistics. So you have the example here in the code. Please go through it. Take your time to essentially go through it. So we have this CES-D depression score, which is a scaled depression score. I'm not qualified to say much about it. Well, I'm actually saying nothing about it. It's a depression scale that quantifies depression, and it's based on a survey, 20-item survey, I believe. So we have read SPSS, summary, the CES-D. We're getting CES-D for homeless and non-homeless. We see already that the median and mean is not too far apart. So you could hypothetically assume it's somewhat normally distributed. It is indeed for homeless individuals. The score seems to be a little higher, but not dramatically high. It's like 4 points. Standard deviation is not different. So I think we're looking at something with a good sample size could be significant, but we will see, right? Good. So now we're plotting this out. Power MF row. We have talked already about the power MF row. I recall. So this is basically how you can get things with on one PDF. And I think I've shown that in one of the earlier classes. So we basically with power MF rows, so C indicates concatenate, indicates that there's more coming in the parentheses. So we have 3 indicates 3 rows, 1 indicates 1 column. So this basically gives here MF row will now align these graphs in 3 rows with 1 column. So now depicting the same thing with a so-called density plot, we essentially were seeing the same data shown with the density plot, where it basically reflects the probability of being in a certain region. So you essentially see here that the mode of this data is shifted to the right, that homeless again seem to be somewhat more likely to be depressed. Then on the other hand, you see that this is very plateauing, while the mode is a little higher here in the lower stages. It's also the variability is wider, but then on the other hand, the low entries, less entries here. So the probability is definitely shifted as a whole to the right. And this is also seen when you look at the median. You see the median here in the box plot, slightly higher than on the non-homeless box. And essentially you see that this is higher. So I always like to recap at this point whenever I see a box plot is, I always want to remind people essentially what they're looking at. So what do you see here? You see on the box plot, you see a median, right? You all know that the middle line is the median, it's not the mean. We see the box. The box is essentially limited by Q1 and Q3. In between you have Q2, which is the median. It's 50%. 50% of all the data is below that, 50% is above that. Q3 is 25% of all data is in between the median and Q3. 25% of our data is above Q3. Same here, you have between Q2 and Q1, you have 25% of all the data. Below Q1, you have 25% of the rest of the rest 25%. What are we looking at with the whiskers? And this is a conversation piece, and I'm circling back because so many people are mixing it up. So what you have essentially is the whiskers indicate nothing that has to do with the outliers or whatsoever. You see outliers beyond that. This is Q3 plus 1.5 times the IQR, where the IQR is Q3 minus Q1. So the whisker is Q3 plus 1.5 times the IQR. In the same fashion, it's Q1 is 1.5 times, it's minus 1.5 times the IQR. Good. And here you still see outliers, so it has nothing to do with outliers. Okay, it does have something to do with outliers, but not as much as you would think. So, but this is the correct answer. All right, good. Let's move on. So describing the covariance and the potential confounders, we'll work with the following covariates for now. So we use age, gender, and race group. Descriptive statistics, we do mean and standard deviations with the percentage of discrete variables being produced. We present the testing of those variables across the two study groups of the study variable. Such testing is to inform how each variable differs across the two groups of the study variable. It should not be used to identify or classify if the variable is confounded or not. So you cannot say whether a variable that differs between two groups is a confounder. You just don't know. You could hypothetically, arithmetically approach this, and you could say, okay, so is there correlation between exposure and outcome? And you could kind of conclude based on that. Can you say with certainty? No, absolutely not. And you will see that because here we have the t-test, right? So we're looking here at age in different conditions. So we have a mean of, oh, look at that. Hold on, sorry. Sorry for that. And so it's just something got my attention because it cannot be t-test. Harmlessness. Okay. Yeah. Okay. Okay. Something caught my eye. You see, when you run this, you get here a mean of x and a mean of y. And this is obviously a problem with the coding. So you want to replace this comma, and you will have it in the one that I'm uploading. You want to replace this comma with a tilde. So essentially what the t-test here shows, it's like it's age as a function of homelessness. So it basically will change it and look into the age in group 0 versus group means and group 1. So these that are homeless actually do have higher age and do have a higher age. Okay. So this being said, so there are differences. We have the chi-squared here. The chi-squared can be done in that fashion. There's nothing that contradicts that. We could hypothetically make this a table. So it comes to the same thing. That recognizes it. It's just always good to double check things second time. Okay. Good. So just always pay attention to these tiny little things, right? So this, what caught my attention is because I wanted to know the mean and I wanted to know whether it pointed in that direction that I said it did, and I found that it was not. So always be a very diligent observer, whatever analysis you do. But sometimes, so my boss always keeps on talking, the boss and mentor keeps on talking about the so-called canary in the coal mine. And this is really what it is. I don't know whether you know the story, but the gold miners in South Africa, they brought the canary birds down in mines, and they observed the canary bird while they were working and digging for mining for gold. And when the canary bird fell off his little branch and stopped tweeting, they knew that they had to leave immediately because the carbon dioxide, the toxic fumes were just getting too high and they were in immediate danger. So as this being said, why am I saying this? Because when you see something in your analysis that just cannot be, you cannot just ignore it. This is a mistake that you sometimes make in the beginning, and you basically assume, okay, it's all going to be fine, and like down the road the error is going to disappear, and you don't appreciate the mistake what it is. Every mistake you make at every stage of your analysis has a reason, and that reason most likely it's going to bite you later on. It's very unlikely it will not. It's to be honest, it's like you can create a lot of confusion by accepting things that a trained eye would have rejected as being impossible. So like right from the start, when you start coding, when you start analyzing, always pay attention to the details and make sure that you jump on everything that is kind of aberrant or abnormal right from the get-go. And make sure you understand it. I'm not saying it couldn't be, right? Something that cannot be can sometimes still be. So just because you're seeing something that doesn't make sense, it doesn't mean it's wrong. You just gotta be sensitized towards accepting things only if you have triple, quadruple, quintuple checked everything ad nauseatum, and to an extent that you're really 100% certain that you know what you're looking at. Okay, so now I rambled on about a whole different topic, but essentially this is what we're talking about. So we have a chi-squared test. We have potential confounders, race group and females. We have a confounding model based causal inference, which is the simplest unadjusted effect. We are looking now at homelessness. Let me go full screen again. So we're looking at homelessness again. Homelessness estimate 2.184. So that means, let's go back. Let's see again what this means. That this difference should be consistent with the mean in the t-test. Obviously not that one. So we have here a difference of 36.3 at let's cut this down. Minus this, minus 1.34. Oh, that's 8. CSD. So here we have this and this. This is 2.18, which is exactly synonymous with that. Goes in the same direction as what we have done in previous lectures. So the difference essentially is consistent with what you see on our linear regression model. So now what else? We're testing now for additional parameter. We essentially lower now the effect. The estimate gets smaller because age, gender, and race already has influences. And we're getting closer. So we have a propensity score that was developed by running a logistic regression model, where the outcome variable is a binary variable indicating the study variable. So what covariates should they include? For the matching, you need to include a covariate that is related to both the study variable and the outcome, which is the very definition of a confounder, right? These three demographic variables, age, gender, and race, are unlikely to capture all covariates that should be included, but it goes at least in a direction. So you will then see empirically what covariates are still significantly different. But basically, you can also try different models, and you can try to essentially do better. So in the lab, for example, we will do different models, and we'll try to do a different model. So this propensity score essentially is now calculated by using, just like in the previous way, a generalized linear model, using homelessness as the outcome, including age, gender, and race group as covariates. It falls in the family of binomial models and binomial outcomes, and comes from the data DAT. And in the summary, it looks in this way and fashion. So essentially, we are getting significant outcomes for white, which essentially comes at interesting. At an increased odds of being homeless. I didn't think that would, because it has to do with the sampling. Okay, let's think about that more. Okay, so female has a protective effect, age, slightly borderline-ish, but with a small magnitude, Hispanic, other, and white. That's so interesting. I don't know that. Okay, but significant for white essentially. So using this model, we can now calculate the propensity score for each individual. It's basically the predicted probability of being homeless given the estimates. So we are predicting now the propensity score. So we're doing PR score is now predict MPS type response. Homeless is homeless. So we get essentially, you get what the predict function, you get an outcome for each dimension, right? So you can now examine the region of common support of the scores. And you can now find pairs of observations of very similar propensity scores based on certain measures of similarity. And you can do this with the package match it. Package estimates the propensity scores and background matches observation based on a method of choice. So this is the code for doing that. We're loading the library match it. The library deploy is needed because we want to pack it into a new package. So we're using select, CSD, homelessness, and age, female, race group. Then we match it on these, and we get here method nearest, which is essentially the nearest method, so there are different algorithms. We are replacing. Replacing means that from the larger group, you would essentially have a probability to get the same individual again. So you need to switch this off. I think the default is also false. And then you get essentially, so this has to do with the matching weights, which is set into 1, and then we have the data. That essentially comes here. So summary, with summary and plot, you essentially can compare now how successful the matching was. You can compute a table 1. Okay, remarks, matching was done without replacement. We'll talk about that. The one-on-one matching was performed, therefore no change in the weights. So that is the matching weights. Nearest for nearest neighbor matching. And manual of matching for different matching algorithms other than nearest. So now we examine the match data. So now we want to see how does it compare. We are building now a new data frame containing only matched observations. We're getting a significantly smaller data set, which is not too bad. We're only losing like 35 entries, which is not terrible by no means. I've seen worse. I've seen worse than that. So the problem obviously is that not enough, particularly when you use the replace false function. So replace true would basically get you duplicates in your control group. So usually the control group will be larger than the intervention group in many use cases. If you would replace true, you essentially you run into the danger of having duplicates, and with sufficient sample size and sufficient balance between the sample sizes between the cohorts, I would not ever choose replace equals true. Replace equals true is really a rather rare use case. I would not really do it and not recommend using it, except for if it's really definitely necessary. So we have 418 observations. That essentially gives us 209 pairs of homeless versus non-homeless. The final data set contains a variable called distance, which is the propensity score. So this is the actual distance from having a probability of 1 to be homeless. So we will now do 2 things to examine the covariance balance in the matched samples. We will do visual inspection, and we will do differences in means for continuous covariates. So this is the covariate age. The propensity scores are essentially distributed in this way and fashion. So it is a linear fashion, as you can see. It's a linear relationship they're creating. But you see, and this is interesting, you see quite distributed kind of frequencies between the various groups, between homeless and non-homeless. If you do a comparison of the means, you can just compare the means from each other, which have here to some extent improved. Then you can estimate the treatment effects. Essentially, you do here with a regular LM, a linear model. You do this depression scale as a function of homeless, data equals data M, weights. In this case, not really necessary because the weight is M, and we said we are setting the matching weights to 1. This is also what will go here into this model. You can change that, and you can have them calculate weights. Creates a little bit of a different scenario and will require for you to also use different population designs. So now we need to estimate standard errors while accounting for pair memberships using cluster robust standard errors, and this basically can be extracted from using coef test from the element test of fit 1. So if you look here at the standard error, this essentially will be now analyzed without the covariance. That's also important. So you have matched now the covariance, so you will not use the covariance anymore. So you basically what you're looking at, and if you remember now, so let's remember 2.02871. Let's go back to the first model, because now that's the propensity score. So this is the first model of 2.0274. And this is the raw unadjusted model of 2.184. So essentially that reduction in the estimate of homelessness is now 2.07 is now consistent with the outcome. This is actually smaller, but it also points in the same direction. So the standard error is now more consistent with what we have seen. It's smaller than what we have seen before because of this lack of variability, or this reduced variability, and we're seeing a smaller estimate because of accounting for the effects of age, gender, and race. So this is lab 11. So we will try to, I will walk you again through the code for this propensity score matching. You're being asked to come up with a different model, and you will show the assessment of the covariant balance by visual inspection of differences of means. You will estimate the treatment effect of homeless along with your interpretation. And you will repeat the exercise using different matching algorithm. So this is considerably simple as a lab, and you will see why I'm saying that. Okay, sounds good. All right, thanks for your attention, and hope you found this sufficiently insightful. And I will see you in the lab. Well, I don't see you in the lab, but you will see me in the lab. Bye-bye.